Welcome to Unit 6, Review of Linear Systems with Graphene. And by review, very quick review. A lot of what we see in Unit 6 here, we saw in Unit 2. It's just dealing mostly with two equations, two unknowns. We will then expand that out further into the linear programming area where we may have more than two equations and more than two unknowns. And once we start using Excel with solving these systems of linear equations, doesn't matter how many unknowns. We won't be able to graph it if there's more than two unknowns, but you know, that's what it is, right? So we're going to solve linear systems consisting of two equations. So we did this in Unit 2, right? We had the Unit 2 word problems. Often there was two relationships, two variables, and we solved that, right? And you know, we got that down, right? And if not, go review give the Unit 2 stuff another little look. Okay, so we're going to graph these, okay, just so that we can kind of get an understanding for how the relationships are relative to each other. And that's it. So really, this will be a quick review of solving these problems, and then a little bit of graphing, because graphine's usually not done too much in high school, and when it is done, they get you to do that TI-83 stuff. Okay. So we learned in Unit 2 that if you had two equations and two unknowns, you could solve that for a unique solution. Okay? Just like if you have one equation and one unknown, you can solve that for a unique equation. And then as you expand out, three equations, three unknowns, four equations, four unknowns, and so on. Okay? So when we solve for these systems of linear equations, essentially we're finding the intersection of the two lines, right? And so when you read that second bullet and you're going, solving a system of two equations requires finding a pair of values for the two variables that satisfies both. And you go, okay, that's nice. But really all it means is, where do the lines cross? Boom, intersection point. That's it, right? Solutions happen at intersection points. And that'll be a theme as we move into linear programming. Solutions happen at those intersection points. Okay, so when we solve for a system of linear equations in Unit 2, and we'll do a little bit in Unit 6, we're essentially finding the intersection between lines. Okay, that's crucially important. It's crucially important to us. Okay? All right, let's do some practice. Okay, so let's solve this particular problem. And so I'm just going to write it out here just so that we can see what's going on. Well, forgive my messy handwriting. PowerPoint saved my career. If I had to write on the board all the time, it would be painful for both of us. Okay, so before, when we were in Unit 2 and we did this, you know, we'd come up with some common multiple of either both of the x coefficients or both of the y coefficients. This one looks messy. It's got decimals in it. So I kind of drop back to sort of the lazy way of doing it rather than too much brain sweat. So if I just multiply the first equation, so I'm going to eliminate the x. So if I multiply the first equation by the coefficient for the second equation, all for x, and then multiply the second coefficient for x by the coefficient for the first x. Oh my gosh, it sounded like a lawyer. We know that 2.5 times 6.5 is the same as 6.5 times 2.5, right? So that's the easy way to do it. We just have to remember, it's easy to forget, we're going to multiply everything by these, not just the x's, but we have to multiply everybody along that given equation by the same number. If we do that, we've just preserved the essential relationship, and we're okay, right? We've changed the numbers, but we haven't changed the relationship. Okay? So when we do that, our equation number 1 comes up with 16.25x plus 8.75y, and that equals to 320. Again, 16.25x then, plus now 29.25y, and that equals to 689. That's my equation number 2. I like the positive numbers because I don't want to have to worry about, did I remember to put the negative in front of this coefficient or this number or not? I mean, inevitably it happens, but I'm just trying to keep myself a little bit head straight. I'm recording this on a Saturday morning, so, let's keep it simple. So I'm just going to go equation 2 minus equation 1. Okay, just so I have a positive coefficient in front of the y, and I have a positive number on the other side. Had you done it 1 minus 2, it won't change any. Eventually, the negatives would have canceled out anyway. Okay, so when I run through this, I get 20.5y. Of course, the x's have dropped off. Equals to 369. Y equals to 18. Okay, now I take that 18 and I substitute it into one of the two original equations. Okay, just for simplicity, I'm just going to pick the first one. Nothing magical about the first one. If it looked like one was a lot easier to use than the other, I would use it. But these look like they're equally messy, so I'm just going to pick the first one. 18, and that equals to 128. And then I go through the process of expanding that out. 63 equals to 128. So we know I'm going to move the 163 over to the other side, to the right-hand side. When I do that, its sign changes from a positive to a negative. So I have 6.5x equals to 65. And wow, I can figure that out in my head. X equals to 10. Okay. If I've got time, I'll take the 18, I'll take the 10, substitute it into maybe the second equation, and see if it all balances out. Okay, and so that's question 1. Let's move further into question 2. Question 2 has got nasty little fractions in it. Okay, so I look at x over 4 plus 3y over 7 equals to minus 2 over 21. That's my first equation. And then my second equation is 2x over 3 plus 3y over 2 equals to minus 7 over 36. Okay, fractions. I'm going, oh, crap. I hate fractions. Fractions are messy. Decimals, I punch the daggone thing into my calculator, I get something. Fractions, oh, my heart's starting to race now. I'm looking at my health check thing. Ooh, boy, don't do any more fractions. Alan, you're too old for this crap. So first thing what we're going to want to do is we're going to want to try to get rid of the nasty fractions. Okay, so if I look at the very first one, I want to find a common sort of a common multiple of 4, 7, and 21. Now, I don't know of a better way to do this, but being the humble, simple guy that I am, I write 21. Does 4 go into 21? Does 7 go into 21? No. I've picked the biggest number, by the way. Okay, so let's look at 42 then. Right? Just doubled up the 21. Does 4 go into 42? No. 7? Yeah, 7 does. 7. And then I keep going. How about add another 21? 63. Well, 4 doesn't go into 63. How about 84? Ooh, 4 goes into 84. 7 goes into 84. 21 goes into 84. Awesome. Okay, so there's my new denominator. So what I'm essentially going to do is, okay, now 4 goes into 84 21 times. So I'm going to take 21 over 21, which we know it's just 1. And I'm going to multiply that by the x over 4. And then I'm going to go to the 7. 7 goes into 84 12 times. So I'm going to go 12 over 12, which is nothing more magical than 1. And then 3y over 7. And then I'm going to go to the last one. 21 goes into 84 4 times. So 4 over 4. And I get minus 2 times minus 2 over 21. Okay, so I'm just multiplying stuff by 1, right? So not changing anything. So what ends up happening here is I get 21x all over 84. And I get plus 36y, again, over 84, plus, oh, sorry, plus, equals to minus 8 over 84. Okay. So now I can just multiply by 84. That all drops off. Okay. And I end up with 21x plus 36y equals to minus 8. Okay. So there's my first equation. Okay. Now I'm going to do similar kind of approach when it comes to the next equation. Oops. So the next equation, which we had, is 2x over 3 plus 3y over 2 equals to minus 7 over 36. And I look in it for a common multiple. So I think 36. Okay. 3 goes into 36. Awesome. 2 goes into 36. Okay, so I'm all set with this one. Right? I'll be able to go 12 times 12 divided by 2x over 30. Sorry, I'm jumping the gun here. Jumping the gun over 3. Plus, then 2 goes into 36 18 times. 3y over 2. And then the number just is the number. Okay. So this comes 24x over 36 plus 54y over 36 equals to minus 7 over 36, right? Multiply by 36 just to get rid of the denominator. Multiply everybody by 36. And now I have 24x plus 54y equals to minus 7. Okay. That's my equation. I then think of my other equation, which was 21x plus 36y, and that equal to minus 8. Okay. So at this point, it's the same as a Unit 2 problem. Okay? Right? Get rid of one of the variables and solve it. Now this one's a little bit messier. I will grant it, it's a little bit messier. If try working this out, if you kept it as fractions, that would be cleaner. Y is approximately 0.185. It's a little bit of rounding, okay? And x will be approximately minus 0.698, okay? I rounded to 3 decimal spots, so it won't get you exactly the right answer. The exact answer will be something like a fraction, but this is really good practice. It's a tricky problem, so if you can solve this system of linear equations without much trouble, or even if you have a little bit of trouble but you're still able to accomplish the task, that's great. Okay, so that'll help you quite a bit. Okay, and that is that. Okay, so let's finish up here with just a little bit of graphing. Okay, now I'm going to just kind of try to keep the graph somewhat simple, but you know, we'll get the idea of how these relationships are working. Now, often when graphs, especially in the era of electronic assignments and so on, the graphs there tends to be a graphing tool. And so the straight line itself is drawn by the technology. However, we need to find 2 points to draw that line. So any linear line can be drawn once we know 2 points on that line. Now, it could be any 2 points. And there are some choices on what those 2 points can be, right? Often, a nice choice is the x-intercept. Okay. Another nice choice is the y-intercept. Why are these nice? It's because I set, for the x-intercept, I'm essentially setting y to 0 and solving for x. Right? Well, that's pretty easy to do. And the same kind of idea with the y-intercept. Now, with some tools, and I'm talking about online assignments here, they don't let you pick a y-intercept or an x-intercept that's non-integer. I don't know why. We draw it by hand. We don't care. But sometimes there's some limitations on software. And if you have limitations on software, what is also on that line? The intercept. Intercept. The intersection. The intersection's on both lines, right? We just talked about that 2 seconds ago. So you find an x-intercept and the intersection. Done, right? Okay, so if you can't find the y-intercept, you find the x-intercept and the intersection between 2 points, and you're all set, right? Because that line will go through both of those points. And then the intersection can be used with the other equation, and you just have to find one of the intercepts over there. So that's a great choice, right? But you'll see how easy just finding the x and y intercept can be in a second here. So let's look at the first equation. 6x plus 3y equals to 300. Okay, so I think of the x-intercept. So x equals to 0, right? Boom, x is gone. 3y equals to 100. Holy cow, that's just like coming into my head. Ooh, look at how smart I am. And then I do the same thing with the y, right? If y is equal to 0, boom. Got 6x equals to 300. Even that one I can do in my head, right? Or quite easily with a calculator. So there's my first set of intercepts. Not too hard, didn't even break out any brain sweat or anything. Okay? And I do that with the next equation. 4x plus 8y equals to 160. And where x is equal to 0, then I have 8y equals to 160, so y must equal to 20. And if y is equal to 0, then I have 4x equals to 160, and x equals to 40. So now I could draw my lines. I could draw my lines on my graph, and I'll just do a really rough graph here. I have my x, I have my y. And so I look at my first intercept. X is equal to 0, y is equal to 100. That's up there. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then I look at x is equal to 50, y is equal to 0. 10, 20, 30, 40, 50. Always better to draw this with a ruler. I don't have a ruler handy. I don't know what the heck happened to my ruler. It's probably locked in my office, and my office is kind of all shut down on the COVID deal. So I just have a hard straight surface, and I draw a line between the two. Look at that. I'm just going to label this. This will become kind of important later on when we start doing linear programming. Let's do the next one. X is equal to 0, y is equal to 20. There we go. X equals to 40, y is equal to 0. Draw the straight line. Make sure I label it. And again, when we get into linear programming, it's always nice to know which lines we're talking about. And that's it. There you go, graphing in a nutshell. Find the intercepts, draw a straight line between the two intercepts, and you're done. Linear lines are awesome. Very awesome. Okay. Let's do one more problem. So here, I'm going to do question number 2, because question number 2 is a little bit trickier than 1. But question number 2 is just an excellent segue into linear programming, okay? Because it sort of it's a very linear programming look to the question, very preliminary feel, and it's just a wonderful question. So a company has two plants, plant 1 and plant 2. Product 1 requires 3 hours of processing time at plant 1 and 4 hours at plant 2. Product 2 requires 4 hours of processing time at plant 1 and 6 hours at plant 2. Plant 1 has 30 hours of processing time available and plant 2 has 40 hours. Oh my goodness. Whoa, my head is spinning right now. I'm feeling a little bit dizzy. What the hell? Okay, either this is confusing or I have COVID. I don't have COVID, by the way. How many units of each product will the company produce? Okay. So I'm hyperventilating because there's so much crap going on in this question that I start to think, okay, basics. Ooh, deep cleansing breath. And I think, okay, what do I not know that I want to know? Right? Now, what am I supposed to solve here? Right? What are they asking me? Well, I look at the very end and I see how many units of each product will the company produce. Okay, so my variable is how much will we produce? So for instance, let's make I amount of product, amount of product 1 produced. And for lack of a better word, a letter, B, the amount of product 2 that's produced. Okay, so I need the variable. I need to know what are we actually solving for, because without that, I can't set anything up. That's the case with this question here. That was the case in unit number 2, and that is going to be the case in linear programming in a big way. Okay, so now I know what I'm looking at. Okay, so let us look at. So I am going to arrange things in sort of a matrix fashion, and only because it's going to become kind of important later on. If I think of my product 1 and my product 2 that I'm producing. Now, where am I producing this? I'm producing this in the plant, right? And I'm producing it in another plant. So 2 different plants. So when I look at product number 1, I say it requires 3 hours at plant 1 times by the number of product 1 I produce. That's how many hours the product 1 line consumes at plant number 1. Right? Now plant number 1 also, right, another word for just saying plus, also is used by product number 2. And I look at product number 2 and it says it requires 4 hours of processing time at plant number 1. So 4 hours times by the amount of product 2 that's produced, that gives me the total amount of plant 1 time that the product 2 line consumes. And this, or the amount available, is 30 hours. And then I do the same kind of thinking with plant number 2. I see that plant number 2, at plant number 2, product 1 consumes 4 hours of time. And again, times by the number of product A that we produce gives us the total amount of time that product 1 spends at plant number 2, plus, and I look at the 6 hours of time that B or product 2 spends at plant number 2. Now, how much do we have plant number 2 time do we have? We have 40 hours. So now I look at that. That's just a system of linear equations. That's unit 2. That's stuff we just did 2 seconds ago, right? Now I solve for the intersection of that point, those 2 lines. What does the intersection of that point of those 2 lines represent? The number of product 1 and the amount of product 2 that we should be producing, right? So I look at that and I go, okay, what's a common multiple of 3 and 4? And 12 pops up. I just multiplied the 2 of them together, right? So I take the plant A, I multiply it by 4, and I get 12A. Multiply by 4B, 16B, equals to multiply by 4, 120. And then I multiply the second equation by 3, right? And I get 12A plus 6 times 3 is 18B, and then 140 times 3 is 120. That's equation 1. Here's my equation 2. And then I'm going to go equation 2 minus equation 1 because I just want to have a positive coefficient. I get 2b equals to 0. Ooh. B equals to 0. And I'm going, oh crap, what the hell did I screw up? What is going on here? Like 0? I've not got a 0 before. What the hell? All that means is we don't make any product 2. That's it. Okay, the product 2 business, we're done with it. We don't want it. Right? We're out of that business. Okay? We're all product 1 all the time. So that's okay. 0 is fine. 0 is fine. And so I take that 0, put it into one of the 2 equations. Let's put it into the first one. I get 3a plus 4 times 0 equals to 30. A equals to 10. Go through. Check it. Double check it. Triple check it. Whatever. You'll see, hey, it works. So we're going to produce 10 of product 1, none of product 2. That's what we should be doing. And you know what? Sometimes we're going to have questions where we're not going to produce in a certain product line. It's just not going to work out for us. So question 1 proceeds very similar to what we were doing before. We're going to need to draw some lines. So if we look at x minus 2y, now I'm going to draw the line first, and all the line means is I ignore the inequality. I need to know where it equals to 4. Okay, and so I'll find the intercepts like we did before. X equals to 0, minus 2y equals to 4, which means y equals to minus 2. Okay. And then where y is equal to 0, x is just simply equal to 4. Okay, then I'm going to look at the other formula, and the line is just where x, again ignoring the inequality, just x equals to minus 3. Okay, that's it. Right. We'll worry about the greater thans and less thans at the very end. Okay, so let's just draw a really rough sketch of this. I kind of know that I'm going to have a negative on the y, a negative on the x. So I'm going to go with really rough 4 quadrants here. Right? Still have the x, still have the y. Okay, let's do the simple one first. X is equal to minus 1, minus 2, minus 3. If x is equal to minus 4, does it matter what y is equal to? No, it doesn't, right? So x is equal to minus 3. It's just an up and down line. X doesn't change, but y can be whatever it wants. And then when I say x is greater than minus 3, I look at the origin. Right? Origin is easy because it's there, right? 0, 0. And I go, okay, which way would greater than be? Would it be to the right of this line or to the left of this line? Well, 0, 0 is greater than minus 3. So 0 is greater than minus 3. So greater than is to the right of the line. Okay, let's do it for the other one. Maybe a little more tricky. So x is equal to 0. So the intercept x equals 0. Y is equal to minus 2. So minus 1. Minus 2 there. Okay, and then where x is equal to 4, y is equal to 0. So let's go 1, 2, 3. Sorry, I'm kind of an idiot. Where x is equal to 4. 1, 2, 3, 4. Y is equal to 0. So, pulling out my pseudo ruler. Look at that. Rustic, because I just can't be bothered to go buy a new ruler. Okay. Now this one is now the 0, 0. So I think of this is where x minus 2 is less than 4. Okay. So less than 4. So if I look at 0, 0, so I basically take the original equation and I plug zeros into there. X is a 0, y is a 0. Okay. So if 0 minus 2 times 0, okay, which is ultimately that answer is going to be 0, is that less than or equal to 4? And you go, well, yeah, that it is, right? So it's actually It is less than or equal to 4. So the inequality suggests that that is an area above that line. And that's it. That's it. So follow the little two-step process, and everything works out quite nicely. And that sort of wraps it up. Okay, so key thing is we're going to use these equations, the system of at least 2 equations to do a lot of our linear programming, and often we'll have more than 2 equations. We can solve it by graphing, finding intersection points. We'll also we can solve it algebraically by just solving it as a system of linear equations like we've done, and find the intersection points. And then ultimately we'll build up to using Excel solver function when it's a multidimensional problem. Okay, thank you very much.